Okay, let's get started. Okay, I see 12 people. Okay. Can I see more of you? How about I just say that, everybody who shows up on video gets some credit for class participation and the rest don't, right? Maybe that'll make sure that everybody feels more comfortable opening, you know, uh, being there in the class at least most of the time. Okay, so let's pick up from where we left off in the last lecture. So a couple of things that I want to bring to your attention. One is that there is a, uh, practice test that's available on Blackboard that you can take using lockdown browser so that you can uh, check your setup, right? So you want to make sure that your browser setup is, works for, when you take the exam next week. So please check that out. So although I call it a practice test, the test is really not the main thing there. It's really how do you do this lockdown browser? How do you use it in order to take a test, right? So the questions themselves are not necessarily useful or representative. It's just that you need to go through the process of taking the test. And I posted a couple of articles on Piazza about taking the test. So go through those guidelines and try to follow them when you take your practice test. And if you have a difficulty remembering all the guidelines, well, you will get better if you take it another time. And of course, nobody's perfect. And so even during the exam, you may make some mistakes. And that's something that, we uh, will deal with when it happens. So don't worry too much. Don't let it stress you out too much. But do try to read the guidelines carefully and follow that as much as you can. So in addition, I have posted 3 sample midterms on Blackboard. Okay, so you should you have exactly 1 week to for the test. So during that week, there are 3 things you do in order to prepare. One is to go through the lecture slides, right? So you can't possibly sit through the lectures, the recordings again, but you can definitely review the slides and try to understand the material that was covered in the slide. So that's number 1. Number 2 is you go through and try to redo your homework problems, right? Try to solve them again, including the problems that the TAs basically did in class, right? So that's the second thing you should do for preparing for the exam. And the third thing is go through these sample midterms, okay? I'm not saying this in this order to suggest that do the first 2 things, and if you get time, do the third thing, right? So you should definitely do all 3, okay? And if you don't get the time to solve, to look through all the sample midterms, make sure that you look through at least one and preferably two. Okay, and those of you who want to do well in the test, of course, should try to do all three, right? So any questions?
I had a question.
Yeah, go on.
Someone else was talking. They can go first.
Was there anybody else? I only see one
Oh,
hand
I
raised.
could have sworn I heard someone, but I guess I'll go. So I was wondering, you mentioned before about getting credit to those who turn on their cameras. I was wondering if that was actually official or not.
No.
Okay, because that gave me a lot of
I'm just
anxiety.
wondering aloud what can be done to, get more people to participate. Because obviously, if we were, if this was an in-person class, right? So everybody will be sitting in the classroom, and it just makes it a little bit easier to.
To be fair, a lot of people participate in chat. That may help with like seeing feedback, because a lot of people have
Right.
anxiety
But as I
with
said,
seeing
I
their
cannot
face.
look at the chat, right? So you cannot say, oh, look at the chat, because nobody, if you want someone to pay attention to what they are, to the lecture that they are giving, it's not possible to be, paying attention to the chat. Okay. So it's, of course, you should use the chat to talk among yourselves. That is very helpful, because you have a question, you ask the question on the chat, somebody else answers, and that's great, right? So that I encourage that by all means. But if you are going to post something on the chat and you expect me to look at that and answer, that's not going to work. Okay. So if I start doing that, then I will be talking gibberish, right? So then that's not good for anybody. So okay, so let's any other questions? Or Joe, was there any other question? Yeah, it doesn't matter what your other teachers do, right? This is how I work. And if you want to be in this class, then you have to live with the way I'm able to teach, right? So sitting in a class and listening to a lecture is very different from actually giving the lecture, right? Actually giving the lecture requires a lot more CPU cycles, right? So it takes a lot more thinking, because I need to make sure that I'm explaining things in a way that is understandable, right? So that's just how my brain works. And so, uh, you know, again, chatting, if we were in a in-person class, chatting is not the option, right? So that is why, we need to find a way that works for everybody. Okay. So, Michelle.
Yeah, I was wondering, so on the test, would we be able to have like a scrap paper to help us like work out the problems?
So whether you will have access to some, okay, so I haven't entirely decided how the test is going to be given, but it's very unlikely that I will say you can't use a piece of paper to work on. Okay, it's extremely unlikely. So you can assume, for all practical purposes, that yes, you will have access to some pieces of paper that you can work on. Okay, so what I would want you to do is, when you take, so the first step in taking the test using the lockdown browser is that you show your ID, and you take a video of your environment, right? And at that time, you want to make sure that if you are using, 2 or 3 pieces of white paper, you want to, make sure that you show that it is, all you have on you is 3 blank sheets of paper, right? Just make sure that the camera goes over those blank sheets, but otherwise it should be okay.
Okay, thank you.
Any other questions?
You mentioned an ID. Is like a driver's license okay?
I am sorry, your audio was well, broke up for a second. So can you repeat it again?
Yeah, you mentioned ID. Is a driver's license okay?
Oh yeah,
Okay.
definitely.
I didn't know if it needed to be like Stony Brook ID.
So show some form of ID, and if you don't have any ID, then let us know in advance, right? So if you, for instance, have a high school ID, well, that's fine, right? Because at this point, if you are on campus, well, then you would have a university ID, and that'll be great. But otherwise, we are okay. Any other questions? Very good. So let's pick up where we left off. So we were talking about sequences and summations, and we went through a few techniques for finding sums of sequences. So we will pick up from there and try to finish up this unit today. Okay. And so as I said, one of the places where we will come across these sequences that you need to sum up is in analyzing the runtime of algorithms, right? So here is an example program, or often this is called pseudocode, to say that it is not it's not a real program that will necessarily run on any system, but it kind of conveys what someone is trying to do. So this is a program for printing prime numbers that are less than some number n. Okay, so it's trying to print out all the prime numbers that are less than n, and it has two loops. The outer loop, goes over every number between 2 and n, and what it does in the inner loop is, check if I is prime. Okay, so check if I is a prime number. So that's the purpose of the inner loop. And notice that if I is a prime number, then it will have a divisor, right? So a divisor other than 1, right? And in addition, the divisor, if it has a divisor, then it has to have a divisor that's less than the square root of I, right? So if I has a divisor, right, then that divisor, at least one of the divisors, will be less than square root I. Okay, because you can see that if you take I, and if it is k times L, then at least one of them has to be less than square root of I, and the other one could be greater than square root of I, right? So you can't have both of the numbers being greater than square root of I. Therefore, it's enough to check up to the square root of I in order to find if there is a divisor, right? And the inner loop is simply doing that. So it is trying every number between 2 and square root of I, and it is checking whether this number j will divide the number I that you're checking, if it's a prime or not, right? If it divides, then you say, okay, it's not prime. And what this continuous statement does is it basically goes on to the next I. Okay. Now, if you never get through here, then you will finish executing this loop, and you'll come here, and that means all the numbers you tried so far, none of them divided the number, and then you have you print that, okay, that means it doesn't have any divisor, so it is prime. Okay, So any questions on this? So of course, we haven't, none of you have seen, we have never looked at pseudocode before, but I hope this is not particularly, complicated. And then you can just at least get a general idea of what's going on, right? Okay, so again, if you I'm looking at several of you, so if you just nod, that would definitely help me, right? So please, if not, if you have a question, of course, ask me the question. So so if you look at how long does it take to run, right? So you can see that the outer loop, right, is executed n times, right? So so outer loop is executed for I equal to 2, 3, 4, 5, 6, up to n, right? So for each time you pick an I, the inner loop is being executed square root of I times, right? So if I equal to 2, the first time you are spending square root of 2 time in the inner loop, then square root of 3, square root of 4, and so on. Okay, so let's assume for the moment that what we are trying to do is to count the number of division operations, right? So let me make that clearer, because if I just said runtime, it's not very clear exactly what that means. Let's say that the only operation that in this program that takes any significant time is the division operation here. And then we want to try to count the number of divisions that takes place. And then you can say that, okay, when I equals to 2, then this is going to be executed, square root 2 times approximately, right? Of course, if you look at this, when I equal to 2, it actually doesn't even execute any time. But if you look at least the larger values, then you end up. So for each I, you end up executing square root I number of divisions. So if you say what is the total number of divisions, then you get this number, right? Okay, so that's the sequence we arrive at, and we want to know what this number is, right? So we would like to figure out, okay, what exactly is this number? Okay, so again, this slide simply summarizes what I just said. So essentially, we are counting the number of division operations, which is this summation, right? So remember that the sigma notation is simply a way of compactly representing a sequence like. So we start with I equal to 1 and go to n. So this is square root 1 plus square root 2 plus square root 3 up to square root n, right? So that is what we denote using this sigma notation. Okay. So now you want to know what does this add up to? But unlike the examples we have seen so far, there are no tricks you can use to find the exact answer to this question. Okay. But we can actually use approximations, because you can see that we already did a lot of approximation, as we said, when in I equal to 2, we called it square root 2, but in fact, it only took 0 time because you didn't even go through the loop once. So we already know that these numbers are somewhat approximate. So to get the approximate sum is good enough. So we are going to talk about a technique for finding the approximate sums of sequences. And the technique we are going to use is integration from the differential and integral calculus, right? So the last technique we looked at was differentiation. Now we're going to look at the integration. Now, the technique we discussed most in the last lecture is perturbation, right? So the problem with perturbation is that we don't quite know what perturbation to apply, right? So when you apply it and it works, great, right? It's like magic, and that's good. But you have, most of the time, you don't know what technique to apply. Whereas integration is quite different in the sense so integration is different because it's actually something that works most of the time, right? And so it's something that it doesn't require, you know, this magic. It just works. And at most, what you might have to do is you may have to look up, okay, what is the integral of some function, right? You may not remember, but of course you can always look it up, right? So the reason why it works is because integral itself is something like a summation. Sometimes it's explained as a summation. Sometimes it's explained as an area under the curve, right? So let's try to understand, what is going on here. Okay, so here is a function, right? So f of x, right? So think of this as the x-axis, and this is the y-axis, right? So what we have done is we have plotted the values of function at x equal to 1, x equal to 2, x equal to 3, x equal to n minus 1, and x equal to n. Okay, so some arbitrary function. And now if we want to think about, okay, what we want is the summation f1 plus f2. Okay, this is the summation that we want to compute. Okay, so what I want you to see is that each of these rectangles has a width of 1 unit, right? Because this is 0 to 1, 1 to 2, right? So all of these rectangles have a width of 1, and their height is f of I, right? So this is the height of this rectangle is f of 1, the height of this rectangle is f of 2, the height of this rectangle is f of 3, right? So therefore, because it has a unit width, the area of this rectangle is going to be f of 1. The area of this rectangle is going to be f of 2, f of 3, right? So therefore, we can say that the summation that we want is nothing but the area of the shaded region, because the area simply corresponds to the areas of these rectangles. Okay, Courtney.
What does the summation represent again?
So don't worry about, let's start with the assumption that you want to compute this sum, right? F1, f of 1 plus f of 2 plus f of n, okay? So in the example we had, right, f would be just the square root function, right? So, but we don't want to do something that works just for the square root function. So we want to think of the general case where you want to add up f1 f plus f2 plus f3 up to fn. Any other questions? Okay, so we can see that the summation that we want to compute kind of looks like some area. Okay, so now let us try to relate that to the area that corresponds to the integral of the function f, right? So again, this is the function f that we have plotted. So if we now plot the curve f of x, right? So it might look like this, right? Obviously, because it is the same function on all these integral values, the curve is going to exactly match, you know, the values that we had in the previous slide. And as such, the discrete sum, as it is called, or the summation, right? So this is called the discrete sum to because it is taken at discrete points like 1, 2, 3, and so on, right? And this area under the curve is sometimes called, you know, you could think of it as sort of a continuous sum. But the point is that the definition of an integral, right? The definition of the integral is the area under the curve f of x, right? And you can see that this area under the curve is a close match for the area under, you know, enclosed by these rectangles, right? So the area of these rectangles, right? The area of these rectangles is what we want, right? And instead of computing that, we can instead compute the integral, right? And the integral is going to be an approximation, hopefully a close approximation for the value, the area of these rectangles. Okay, so in computer science, we don't want to just compute approximations, but instead we want to compute bounds, right? So bounds means that we want to say that yes, we have an approximation, but we also know, you know, what is the maximum error in the approximation. Okay, so what we would prefer to do is, instead of just coming up with some approximation, we would like to come up with an under approximation that is guaranteed to be less than or equal to the correct value, and then an over approximation that is guaranteed to be greater than or equal to the given area, right? So that way we can you know, say that the value of the actual value of the summation is in this range between the under approximation and over approximation. Okay, so now let's see how to compute the under approximation, and it's, you have an idea already because you can see that the way this curve goes, it leaves out some parts of all of these rectangles, right? So therefore, the curve is capturing a value. The area under the curve is something that's strictly less than the area enclosed by the rectangles, right? And in particular, we have completely omitted this rectangle. And then in all these rectangles, we have omitted, you know, some part. Okay. So what we can say is that the discrete sum here, represented by this summation, right, will be the first term, which we can just add back, plus the area, right? So now what we are doing is that we are including this area as well. And so this expression represents the shaded area, right? And when you compare the shaded area with the area of the rectangles, you see that all these you know, parts which are vertically shaded, right? So those are not included, right? So therefore, it's clear that this quantity that we compute here is something that is close to the area of the rectangles, but is a little bit less. Okay, so therefore, we say that this is an under approximation of the discrete sum. Any questions? So I do want you to be able to, so as one of the things I mentioned in the last lecture is that the perturbation methods, the results are useful, but to be able to apply or come up with a perturbation method yourself is going to be very hard, right? But when it comes to integration, that's not the case, right? So you should be able to apply integration to compute sums, okay? But I'm not going to, I'm not going to worry too much about whether you can actually do the integration or not, okay? So if I give you a problem involving the computation of a sum using integral, I will tell you what are the what are the integrals of the functions that are involved, right? So you don't have to remember, okay, what did I learn from integral calculus, okay? But otherwise, I do want you to be able to do this. So if there is something here that you don't understand, it's a good time to stop me and ask questions.
So this might just be convention, but so why is it that you include F1 when it could, that's just the same as, maybe you have F1 in the integral, but add F of n?
So, so what we could have done is we could have done the integral from 0 to n. I think maybe that. Am I answering your question?
Or you could have done it to from 0 to n minus 1 and then add F of n.
Yeah, that will be the, we will see that in the next slide.
Okay.
Okay, so you're just, yeah, ahead of where I am. Any other questions?
Well, I'm sorry, Professor, but I guess just like for sake of computation, if you can include F1, couldn't you also say, well, it's easy enough to compute F1, why don't we also include compute F2, and then so on and so forth? Why is it a guarantee?
No, because if you have any, you could always have a finite number of those in the front, right?
Right.
Because that will still be a closed form expression, right? So
right.
You can do that. But when you see the next slide, you will see why we have done this.
Okay, thank you.
Okay, so because on the one hand, we want to come up with a good lower bound, and then we want to come up with a good upper bound, right? That's what you'll see in the next slide. Okay, so now what we do is we slide this whole curve one position to the left. Okay, so what's going to happen is that this point out here is going to move over here. This point on the curve is going to move here, okay? Which is what has happened here, right? So now you can see that instead of the curve ending at n, the curve ends at n minus 1, right? Which is exactly the question that Alexander was asking, right? So we have moved the curve to the left. And if you remember, some of the things that you might have learned in high school, moving a curve to the left means, you add 1 to inside the f, right? So this is actually, we can call it f of x plus 1, but it's not that important because we know that moving the curve to the left does not change the area under it, right? So whatever we calculated as the area under the curve, right? That is still the same even though you moved it to the left, right? So it doesn't matter, right? So we are going to continue to use the same expression for the area under the curve, which is this integral, right? So that integral represents the area under the curve, and we are going to continue to use the exact same formula, okay? But now what we have done is we have left out this whole rectangle. So we are going to add that rectangle plus the area, okay? So this is going to be another approximation where we basically take the area under the curve and add it to f of n, right? But in this case, we do know that the rectangles are all completely contained within the curve, right? So therefore, excuse me.
Bless you.
Thank you. So, so now we clearly have you know, this quantity is clearly more than the area of the rectangles because we include these areas which are outside the rectangles, right? So we have included all of this in this quantity. So therefore, this is going to be an over approximation or an upper bound. Right? So what we had in the last slide is an under approximation or a lower bound. Okay, so so you have a lower bound and upper bound, and then we can say, you know, so essentially what we will do is we'll say that, okay, this is our lower bound, this is our upper bound, and this is the summation that we want to compute, right? So we can say that this value is definitely between these two estimates we have come up with. So this is the estimate, that's the lower bound that we showed on this slide. And this is the estimate, which is an upper bound that we computed on this slide. Okay, so we say that it is between that. And of course, so both of those bounds require you to compute this integral, right? So what is square root integral, right? So square root is nothing but x to the power half, right? So this is, and if you remember your differentiation and integration of powers, then you will see that if you integrate this, you will get x to the power 3/2 divided by 3/2. Okay, and you can check that by differentiating, and then you'll get, if you differentiate this, you'll get square root x. Okay, so so that's the integral we are using, x to the power 3/2. But then we have to apply the definite integral. So we have we apply. So this notation, what this notation means is that you're going to evaluate this function at n, and then you're going to evaluate the function at 1, and then you're going to subtract you know, the value at n, the value at 1 from the value at n. Okay, so that's why you when you apply this, so x to the power 3/2, you know, when you apply it at n, you get n to the power 3/2, and when you apply it on 1, you will get a 1. So you take the subtraction, and this is the integral that we want. Okay, so once we have that integral, then to get the bound, the lower bound is the integral plus f of 1, right? So f of 1 equal to square root 1 equal to 1, right? So remember, the lower bound is nothing but f of 1 plus the integral. The upper bound is f of n plus the integral, right? And f of n is, of course, square root n, because that's the function that we are trying to sum up, right? So if you want to sum up the square root example, we end up with this range. And you know, then if you want to understand this number better, one thing you can do is you can say, you know, what is the difference between these two quantities, right? So the difference is square root n, right? So, or rather square root n minus 1, right? So if you look at this term and this term, the integral is, of course, the same. So the only difference is there is a 1 here, and there is a square root n there. So if you look at the difference, it's going to be square root n minus 1. Okay. Now we can say, okay, so that is the difference. So we can compare it with the value of the number to get an estimate of how far are we, right? So the value is basically n to the power 3 by 2, right? So we can approximate it to n to the power 3 by 2. So we have an error in the range of n to the power half out of a value that is roughly n to the power 3 by 2. So the error is approximately 1 by n, right? So because we did this integral instead of doing the actual addition, our answer may be off by a factor of 1 by n, right? And then you can see from that, if n is 10, 1 by n is going to be 0.1, right? So the error is going to be 10% if the value of n is 10. If the value of n is 100, then the error is going to be 1%, and so on, right? So in general, these approximations are going to be more accurate for larger values of n as compared to smaller values of n. Okay? Any questions? So we went through showing how a discrete sum, which is something like this, can be turned into, can be approximated by using integration, essentially integrating the function f of x, right, from 1 to n. And then we have these two bounds, which the lower bound is the integral plus f of 1, and the upper bound is the integral plus f of n. Okay, so then with those two bounds, we can estimate fairly accurately what the value is. Michelle?
I don't understand what you did at the end. Like, why did you divide radical n minus 1 by?
Okay, so what we are trying to do here is to estimate what is the error, right? So the error is going to be the difference between the upper bound and the lower bound, right? Because the actual value is between the upper bound and lower bound. So the maximum error we could have is the difference between the upper bound and lower bound, right? Now, that is the absolute error. Now, what we want is a relative error, right? Because we want to say, the error is 10% or 5% or 1%, right? So to get the relative error, we need to take the absolute error and divide it by the actual value, right? So the actual value is this complicated expression, but because I'm only interested in approximate value of the error, I approximate this whole number by the most significant term here, right? Because n to the power 3 by 2 is generally much larger than n to the power half, right? So if you take n equal to 10, right? So n to the power square root n would be like 3, and 10 to the power 1.5 will be 30, right? So
Yeah.
therefore, so you see that the term that really matters is going to be this one. So for figuring out the relative error, I'm taking this dominating term as the value in the denominator. So now I say, okay, I'm going to approximate the value by n to the power 3 by 2 to compute the relative error, and that gives me that I have n to the power half in the numerator and n to the power 3 by 2 in the denominator, and that's equal to 1 by n. Make sense?
Yeah, thank
Okay.
you.
Any other questions? Okay, so let's take another problem. So you may remember that early on we looked at the factorial problem, right? So we said, okay, here is a factorial and here is a magical formula, right? So we said n factorial has this magic formula, right? So now let's see if we can get anything like the magic formula. So n factorial is this product, right? So 1 times, 2 times, 3 times, all the way to n. And just like sigma is a notation for compactly representing a sum, pi is a notation for representing a product. Okay, so so that's the notation. But of course, what we have been talking about so far is adding up, and we haven't talked about how to do multiplication. But you know, there is a way to simple way to turn multiplication into an addition, right? So can you tell me how this can be done? How can we convert a multiplication into an addition? If you apply some function, multiplication turns into addition. What is that function? Greg?
Add n times.
So so the Owen.
If you take the log.
Right. So if you take the log, then right. So when you take the log of this, all the multiplications become additions, right? So we just take the log and we take the natural logarithm, which is with respect to the base e, because we want to do integration and so on. And all of those are nicely defined on natural logarithms. Whereas if we try to use logarithm with another base, the integrals become a little bit more, they become bigger, right? So they're just a little bit more difficult to manipulate. So we'll just use natural logarithm. And so instead of estimating n factorial, we estimate the logarithm of n factorial, which is going to be this sum. And so we have this discrete sum of logarithms, right? So once again, we have a similar situation of summation of f of x, where f is the logarithm function, natural logarithm function. Okay, so now you need to know what do you get if you integrate natural logarithm of x and take it as a given that this is the result, right? So if you integrate ln x, then you get x ln x minus x. Okay, so that's the answer. And if you're not convinced, you can later on try to differentiate this and convince yourself that it leads to ln x. Okay, so and then we evaluate this function at n. Okay, and that is going to give this value, right? So we simply substitute n in the place of x. So you're going to get n ln n minus n. And then from that, you're going to subtract the value of the function at 1, which is 1 ln 1 minus 1. But then the minus, there's already a minus here. So this minus is going to turn into a plus. Okay. And since logarithm of 1 is always 0, so you can cross it out, right? So you end up with this expression, n ln n minus n plus 1. Okay. So this is the definite integral, and we know that the bound is the definite integral plus ln 1 on the left, and the definite integral plus ln n on the right-hand side, right? So again, remember, this is our f of n This is f of 1, right? And we cross it out once again here because ln of 1 is 0. Okay, so so we get this bound. So what we are going to do now is we are going to instead of trying to compute the error and so on, let's simply take the average of the two bounds, right? So this is the lower bound, this is the upper bound. So why don't we simply take the average as our estimate? Okay, so that's what I'm going to do. So since this part is common in both, right? So if you take the average, what you're going to get is the common part plus half of the part that's different, right? So you're going to get n ln n minus n plus 1 plus 0.5 ln n. And so what I have done is this n ln n and 0.5 ln n have been combined into n plus 0.5 ln n, and then this minus n plus 1 is here. Okay, so our estimate of the sum of the logarithms is this expression, right? And so what we want to do now is we can then, so what we have is, sigma ln I is approximately equal to n plus 0.5 ln n minus n plus 1. Okay, so now we can reverse the process of taking logarithms, right? So we can raise everything to the power of e. So remember that when we took the logarithm of n factorial, right, that's when we got this summation of ln of I. So if we reverse the process, then this will become n factorial. Okay, then we need to raise this whole thing to the power okay. So what we are doing, reversing the process, is simply one of raising, making this the, raising it to the power of e. So you have e raised to this power, and when you raise the left-hand side to that power, you'll get n factorial. So, and then if you simplify what you have on the right-hand side, you will get, again, arithmetic on the exponent becomes product or division in the number, right? So this is going to become e to the power n plus 0.5 logarithm of n times divided by e to the power n, because this minus n. Okay, so let's do this in a few more steps. Okay, so e to the power. Okay, so then times e to the power minus n times e to the power 1, right? So what I've done is that I've taken the addition in the exponent and turned it into multiplication here, right? So we have this, and then if you look at just this term, right, you can rewrite this by changing the order. So you can say it's e raised to the power logarithm of n, and then you can do whole thing raised to the power, right? So all I did is I interchanged the order, okay? And by definition, e to the power ln n is nothing but n. Okay, that's the definition of the logarithm. Although, you know, you have to look at the definition and stare at it before being convinced. So, but take it from me, e to the power ln n is nothing but n. So this is nothing but n to the power n plus 0.5, right? So that's what I have written. So this term becomes this term, e to the power minus n times e. So let's call that. I'm sorry. Right? So so our estimate is that n factorial is given by this expression, which we can further rewrite in the following way. N to the power 0.5, I have written it as a square root n, and then n to the power n is here. Okay. So n to the power 0.5 is here, and then n to the power n is over here, and e to the power n minus 1 has been separated into e to the power n here, and then 1 e over there. Okay, so I did that because I want you to be able to compare it with the Stirling's approximation, which is written in this form, and you can see that everything matches up except that you have an e here, and there is a square root 2 pi over there. Okay, so we are a little bit off, which is to be expected because Stirling's approximation is based on a more accurate approximation than what we have. But it's instructive to think about what is the difference. So pi is 3.14. So 2 pi is 6.28. And if you know your squares well, then you will know that the square root of this is approximately 2.5. Okay, because 2.5 square is 6.25. Whereas E is something like 2.7, I think, right? So we're not that off, right? So we are close enough. And so that way we can estimate this value as well. Okay, so what I'm going to try something a little bit different. Let's see how well it works. Okay, it's like a kind of like a puzzle, but I need to, you know, try to arrange blocks in a certain way, and we will see how well that works when I try to do it on. So this is, let's see, what do you see? Okay, now. So you have to bear with me because it's quite difficult in where I am to try to set this up. So this is what I'm trying to do, right? So what I'm trying to do is I want to arrange these blocks in a certain way. So for instance, the simplest thing I can do is, my goal is to arrange them like this. And my question is, of course, I can use as many books as I want. My goal is to make this overhang part, which is going, let's see, where am I? You're able to see, right? So, so this is the left end on my side. So what I want to do is I want to push these as far as possible, right? And my question is, how far can I go before it'll collapse, right? And I can do it with just one book, and then you know the answer, right? So I know exactly when I go, I can go exactly half the length of the book. Beyond that, the center of gravity is going to go out and it's going to just fall, right? But what if I used two books, right? It looks like I can go a little bit further, okay? So the question for you is, how far do you think I can go? Is there a limit? Is there no limit? Of course, these are all guesses. So unless you have seen the problem before, you won't know the answer. So this is this is just time for guessing. Who wants to guess?
I think there's a limit.
Okay, so then take a guess at what the limit is. Is it like one? Do you think I can go that far? Some book, right? Obviously, if I use all the books, will I be able to get the topmost book, this far out?
Probably not.
Probably not. Okay, so let's try and see. Okay, so we can try. Let's see how far. Okay, good. So one way to do this is, I try to go that far, right? So you can see that I'm well within half, so it's pretty stable. If I press here, it just comes back, right? So the next one, I can try to, do that. No, it doesn't work, right? So it's too far. So maybe seems stable. Let me try one more. No? Right? So not doing a good job, right? Or maybe that is the limit. What do you think? Any ideas how I may be able to do it? Can I do better than this?
Well, probably if you moved it a little closer, you'd have some non-zero percentage would be off.
So this seems, like it feels like I'm already too unstable. And so I'm not able to push beyond this. So I don't know whether I understood you right or not, but that's my answer. If I didn't understand you right, then say it again.
No, I think you interpreted it correctly. I was just thinking that maybe, like, say you moved it at least, 1/100th of an inch, that would technically be a little further out, but.
Right, so let me just, in fact, it's more stable now, right? And if I put it on top, even if I'm aligned, right, it seems to make it less stable, right? So something is wrong. Can you think of, is there a different way to do it?
Can you move the first book like in some more, and then
Okay.
yeah,
Right?
and then you can move the top book a little to like.
Do you want me to move this book or this book?
That book, yeah, that one. Yeah. So you can move that one further out. Yeah, like that.
Okay. So does that give you a better technique? Is there something systematic that we can do in the way we try this that will give us, more of an overhang?
Would it be that like every consecutive book can get pushed like further out? So like you start with like a small push and then like you keep building as you add books?
Right. So let's start all over. Let's say that, let's say this is the first book. So how much do you want me to push? So tell me when to stop. Stop?
Yes, stop.
Okay, good. Then this one, tell me how far I should go.
Stop.
Okay. Tell me now. Okay, I'll tell you how far I can go, right? I can go, obviously, this far I can go. But obviously, if I go this far, then the next book would not be able to go much farther. So tell me where I should stop. Should I stop here?
Yeah.
Okay, so we'll stop there. And let's go with the same type of thing. And so I seem to have done better, right? Because if you look at my hand here, it looks like almost 3/4 of the top book is out, right? And if I try to extend it further, it's not going to work. Okay, so I'm not able to get the whole book outside. Anybody wants to suggest another tweak on this that maybe will help me go even farther?
Could you make the distance between the books like smaller, like push them in a little more? Yeah, like each one like a little more, yeah.
Okay. Unfortunately, I may have, no, I have one more book. So, yeah, so you can see that it is kind of not that stable, but I can definitely do this. But you can see that in terms of how much overhang I have achieved, it's probably only 2/3 now. Greg.
Maybe we can say something like the closer the book is to the bottom, the less it moves from its from the position from the book below it.
Exactly, right? So that's how we need to start. Okay, so let's do it this way then. Okay, let's move things from the top book, right? So we know that the top book, we can move it more or less halfway, right? We know that only when it goes beyond half, it's going to tip, right? And now we can see how far the second book will go. Okay, so this is how far the second book will go. Okay. Now, the third book, I hope you can see, right? So third book. Okay, so that's how far I could go with the third one. Then the fourth one. So I have, right? That's victory, right? Because now you see that the first top book is completely outside, right? So this is the end of the book, and you can see that the top book, I guess I can move this even more, right? So now it's clear that I managed to achieve, this thing is completely outside. Okay. And you can also see that, if you look at the curve over here, right, it's not really, completely fallen down. I'm still able to get some distance here, right? So probably I can achieve even more, right? So let's keep this aside and let's see what is the summation problem that we are dealing with here. Oh, I should have stopped sharing. You could have told me I messed up, because you would have seen a bigger version than one small view of the blocks.
We're able to change which screen we see. We can actually click on your in-person screen and make that one the bigger one.
Great. Yeah, great. That's great. So let's see. So this is the hanging book problem. So so the first block, we can go halfway when the center of mass of the book will be right on the edge of the table. I didn't really use a table. I used a book at the bottom as a substitute for the table, but let's say the bottom book is the table, right? So this is how it looks for the first thing. Then, was there a question? Okay, so let's see what happens in the next one, right? So we have this block, right? And then we have the second block, right? The way we moved this is that the second block was, exactly at the half of the first one, right? Now we want to find out what is the center of gravity of this combination, right? So the center of gravity is going to be somewhere here, right? And so let's say this is center of gravity is a distance d from this point, right? So this is half of the block, right? So from the previous slide. So let's say that the combined center of gravity is at a point D, and that is half minus D, right? Because this whole thing is half, right? So if this point is at a distance D from this end, then this end is going to be half minus D, okay? So now you can see that the center of gravity is going to be right between the center of gravity of the top block and the center of gravity of the second block, okay? And so this D is going to be right in the middle, so it's going to be 1/4, right? So the combined center of gravity of the two blocks is going to be, let me clear out this part. The center of gravity of the two block combination is going to be 3/4 from the end, right? Because this is half, and we said this is going to be 1/4, okay? And then we can do the same kind of calculation and say, okay, so the key point is that when we place a book underneath, then the center of gravity of the top two blocks should fall exactly at the edge of this block, right? So that way these two blocks won't tumble and fall off, right? So the center of gravity of the top two books should be either at the very edge or slightly to the left of the very edge, right? So then it won't fall. And you can do the calculation, and you will find out that that is, that you end up with a sequence like this, okay? So the first two we saw, one half and 1/4, and then you will get to 1/6, because essentially what ends up happening is that there are two blocks that are pulling the center of mass, right? So these two blocks are pulling the center of mass to the right, and this block is pulling the mass to the center of to the left. But this is only one block versus these are two blocks. So you're going to have the combined center of gravity is going to be closer to the center of gravity of these two, which means that you will get only 1/6. Okay. So the calculation you can see later. I'll show it to you in more detail in the next lecture. So so it ends up being the case that you get this sequence half plus 1/4 plus 1/6 plus 1/8. So what is the maximum that we can get? It's going to be this summation, right? And this is kind of what you saw, that as you went down, the overhang was reducing, but it wasn't completely disappearing, right? So you can see that in these numbers. There's a big overhang of half, then 1/4, then 1/6, and 1/8, and so on. Okay, so now we can add this, and we have the summation again, and the summation, we will, this summation is called the nth harmonic number, right? HN. It's just for your information. It's not relevant for doing the calculation. The summation we have is sigma 1 by I. And then we apply our integration technique. So if you integrate 1 by x, that's its integral is ln x. Okay, so the approximate value of this sum is going to be, ln n. Okay, a natural logarithm of n. So if you have n terms, then it's going to be natural logarithm of n, which is very interesting because what it tells you is that the maximum overhang is infinite, right? Because notice that what it says is that if you have n books, the length is going to be the log of the number of books, right? That's the overhang. So if you have 1,000,000 books, then you can achieve ln of 1,000,000, which is going to be, I guess, something like 3,000. No, not 3,000. What am I talking about? 1,000,000 is 12, right? Yeah, something like 12, right? So you can get, if you have 1,000,000 books, you can achieve an overhang of about 12 books, okay? If you have infinite number of books, well, ln of infinity is infinity, so you can get, you can achieve infinite overhang if you have infinite number of books. Okay, so that's sort of where I want to stop today. So this is, so to summarize what we did, in the last lecture, we were focused mainly on the perturbation method, which we used for dealing with, showing how to deal with geometric progression, arithmetic progression, and another sequence that I call as, yeah, so arithmetic progression, which is just sum of 1 plus 2 plus 3, that summation. And this one is summation of squares. This one is summation of cubes, right? So all of them can be the closed form expression for these summations can be found using the perturbation method. Then we also talked about arithmetico-geometric progression, where you have this I appearing both on the exponent and as a coefficient. And we showed how to obtain a closed form expression for that. And today we focused on integration. So we looked at the square root problem motivated by the prime number program. Then we looked at the factorial and the hanging blocks. And in each case, we derived a pretty good approximate value for the summation using integral calculus. Okay, so that's sort of where, so we are at the end of the class. So if you have questions, please go ahead and, we will, yeah, so if you have a question, please go ahead and ask. Otherwise, use the time to prepare for the midterm. So the material that we cover in class, as I said before, what we covered this week is not included in the midterm, and what we will cover on Tuesday also won't be included in the midterm. Okay, so but roughly a week after your midterm, maybe 5 days after your midterm, I will hand out the homework on the material that we covered in the this week and next week. Okay, so again, if you have questions, there is only 1 week between now and the midterm. So if you have questions, try to bring them to us as soon as possible. Use the Piazza Forum, and so we will of course help however we can help. Okay. Any questions? Okay, very good. If there are no questions, I'll see you Tuesday.